Technology is the great growling engine of change. With such opportunity and blooming enthusiasm, a warm welcome and a very good evening to everyone. I am Shriya Ganguly, Publicity Chief of RAIT ACM, and I will be your host for today's session. We are absolutely delighted to welcome you all to the Distinguished Speaker Program 2025 on Demystifying Quantum Computing Technology.
I think you can enable the slide share option.
Yes, sir, just a moment.
Also, I hope you would make the session getting recorded, right?
Yes, sir,
Yes,
I'll
sir, we
see
are
to it.
doing.
Yeah, sure. So, are you able to see the screen? Hello?
Yes, sir, it is visible.
Yes, sir.
Okay. And am I audible also, right? Okay. So, shall we start?
Yes, sir.
Yeah, so good evening, everyone. At the outset, I would like to thank the Ramarao Adik Institute of Technology ACM Student Chapter for giving me an opportunity to talk to you. And this particular talk is arranged through the ACM Distinguished Speakers Program, which is an initiative by the ACM. I hope that all of you are aware of ACM, which is a globally recognized computing professional body, which is meant for both computing professionals and as well as students. There are above 1 lakh members spread across 170 countries across the globe, and these professionals are interacting with each other, advancing the computing. So the mission of the ACM is to help the computing professionals to be their best and most creative, and also it helps them to connect to the peers to understand the latest developments and hence inspire them to advance in their profession. So I'm proud to be an ACM senior member, and this particular talk, the Distinguished Speakers Program, is made possible by the ACM. And due to the this particular initiative, today I'm here with you guys interacting with on the topic quantum computing. Before we enter into the topic, let us have a quick understanding of some basics. Imagine we have a coin, right? Now we all know that, imagine that the coin does not balance on its edges. That is the condition. So if you see the coin which is lying on a flat surface, it has two states, either state showing the head, meaning facing up, or showing the tiles, on the other side of the coin. So these are the two possible, the scenarios of a single coin lying on a flat surface. Imagine if I have two coins instead of one, then obviously I will have four possible states. Now with both coins, I can have either head state or head tail, or else I can have a tail and head, or one coin showing the tails and another coin also showing its sides. So totally I have four possible states, meaning if I have two coins, I have 2 power 2, that is four possible states for two coins, right? Imagine if I am adding one more coin to this. Now you can observe that there are totally 8 possible states, meaning all permutations of these possible states, if you list, one coin can have head, another coin head, another coin head, like this, all other permutations of 3 different coins. So meaning, if you can notice, the total 8 possible states in terms of 2 power 3, right? So for every coin, 2 states, and we have totally 3 coins. So totally we have 8 possible states for 3 coins. You may be wondering why we are talking all about this, but have some little bit of the patience, then we will see why we are talking this. Then imagine I have n coins now. What are the possible states, total possible states? Obviously 2 power n possible states I will have from the n coins. Now leave the coins. Let us come to the dice. Now we all play with the dice. If you from our childhood days. So if you see a standard six-sided dice, you can see here in the given in the picture various the positions or various states of a simple six-sided dice. Totally, if you notice, there are 6 possible outcomes ranging from 1 to 6. So all the possible states of the dice 1 to 6, you can also see the pictorial representation of it, right? Now imagine I have 2 dice, right? If you see the 2 dice, if I have, obviously you can see all the possible permutations and combinations of these 2 dice, starting from 1 1 1 2, first dice 1, second dice 3, first dice 1, second dice 4, 2 first dice and then second dice, and so on. You can see all possible combinations of this particular 2 dice, right? I have just given it in the form of a simple matrix representation. So the dice 1 to dice 6, and similarly the dice 1 to dice 6, you can see what are all the possible states you can have with 2 dice, right? So meaning, if you look at this particular scenario, first dice, showing the number 4, second dice showing number 3, right? So each die has 6 possible states. So what are the total possible states you have? Totally we have 36 possible states, right? Now if I scale it up, if I increase the number of dice, then obviously meaning, if I have 3 dice, totally I have 216 possible states, right? Meaning, I have each dice I have 6 states, so totally 3, so 6 power 3, meaning 216 possible states. If I generalize it, meaning if I have n dice, there are totally 6 power n possible states, right? So you may be having a doubt, sir, earlier you spoke about coin, now you are talking about dice. Why all this? The question I have here is, how much information can coins and dice can carry? If somebody asks this question, how do you answer this? Imagine that if I want to answer, so let us say, take the colors of the rainbow, right? We all know what is a rainbow. Rainbow has 7 different colors, so my job is take these 7 colors of the rainbow, either you represent them or encode them by the possible configurations of either the coins or dice. So how many dice or how many coins I would require to represent or encode all these possible combinations of these 7 different colors, how many combinations or configurations of the coins are required or dice are required. If you notice, so I require totally 3 coins to represent these 7 colors, or I need 2 dice to represent these 7 colors, meaning I need more coins than dice, right? Why so? So if you notice here, imagine what are the colors we have on the in the rainbow, starting from red, orange, yellow, green, blue, indigo, and violet. So what I'm doing, I'm representing through the coins. If you see here, I need totally 3 coins, starting from head to the head. One coin as a head, another coin as a head, another coin as a tail. So like this, I can represent the colors with 3 different coins. Whereas if you look at the dice, with the 2 dice, I can represent all the colors through these various states of the dice, right? So, with 3 coins, right, I can represent. Imagine if I am taking, say, take an example, color green, right? If you look at the color green, if I take 2 dice, with the first one showing 1, the second one showing 4, I am able to represent the color green. Whereas in the case of coins, I need 3 coins showing, the first one showing the head and the remaining 2 coins showing the tiles, right? So what all these, the coins, dice, and as well as, if I want to encode or if I want to represent something, how many of coins are required, how many of the dice are required. When I am considering this for this particular color example, what all this infers that coin carries less information than dice, meaning you require more coins to distinguish 7 colors of the rainbow than the dice. So you require 3 coins to represent these 7 colors, whereas you require only 2 dice to represent the same set of colors. What all this infers? This infers that something with 2 states carries the smallest amount of information possible. This is the inference that we can derive from the number 1, coins showing head or tails, dice showing their different states ranging from 1 to 6, and using either of them to represent some piece of information or to encode some piece of information called rainbow colors. If I finalize the conclusion, it says that something with the 2 states like coin carries the smallest amount of information possible. Okay, this is also some statement. How this is related or having an implication towards our computing environment. Just for a moment, keep that point in your mind. Let us see about our computers. We all know about our computers, the digital computers. Earlier, computers means the people, not actually the digital machines or mechanical machines, right? From that stage of human computers to mechanical computers and then the digital computers, there is a long history, right? So even when you look back about 60 years back, NASA was using the human computers rather than the digital computers. And subsequently, you have mechanical computers, then followed by electronic computers. It's a really an interesting journey of evolution of computers, starting from mechanical devices to the current day electronic devices, the gadgets that were occupying larger of rooms to the smaller devices that what we are using today, right? And if you look at the digital computers, what was the fundamental unit? It is nothing but the bits. We all know that the classical fundamental unit of the information is the bit encoding either in the form of 0 or 1. That is the fundamental unit. And we manipulate these bits using different logical gates, and then we compute different activities, right? So, so that is what is digital computer, having a fundamental unit of processing the information as bit. So now what is quantum computer? Quantum computer is a device that uses laws of quantum mechanics, unlike the digital computers which are following the classical digital rules. The quantum computers uses laws of quantum mechanics to perform massively parallel computing through various quantum properties such as superposition, entanglement, and decoherence, right? So this is about quantum computer. We all know what is a classical computer. You may still think, sir, you have already gone to the definition of quantum computer, or you are talking about quantum computer. Few minutes back, you said about something about encoding the information. We'll come to that point. So before that, uh, the last slide spoke about we are entering into the quantum computers era, where these quantum computers are based on physical principles called quantum mechanics. What are that particular features of that quantum world? In the quantum world, unlike the classical computers, we don't compute with typical real numbers. Rather, we actually use complex numbers. I think all of you know about set of natural numbers, set of whole numbers, set of integers, set of real numbers. So all those numbers that we know. So now we also know about complex numbers. But rather, so far in computing principles, we might have not used the complex numbers extensively, but whereas in the case of quantum computing, the computation happens through complex numbers. This is one of the feature of the quantum world. Then another second feature of the quantum world is working with the single state to entering into the superposition of states. So we will see about what is a superposition of state in a few minutes later. But essentially, you need to understand that when we say that a bit representing a zero, either 0 or 1, instead of 0 or 1, we may say that, hey, look, my fundamental unit, it's not that it is storing either 0 or 1, rather it is storing some linear combination of both, meaning you are going to have this fundamental unit which is a linear combination of both 0 and 1. Such state is called superposition state. That also we will discuss in the upcoming slide, right? So meaning, when we say that an object is in a superposition state, it meaning that it is simultaneously in the multiple states at a given same time. As I said, you say a classical bit is in a 0 state or 1 state, whereas a superposition meaning it is simultaneously being in multiple states, right? That is also we will see. Next, what is the other feature of quantum world? Moving from locality to the non-locality. This is another interesting phenomenon in the quantum world. Now, typically, if you look at our modern computing, we all revolve around locality of the objects. The simple example what I can tell you is, perhaps when you are reading operating system, we know about memory management. There we would have seen, a memory location which is accessed. Typically, it may happen that the nearby locations are also may be accessed in the next time. So you use such principle to make the memory management. So that is called locality. Whereas in the case of quantum, we move from locality to the non-locality. Meaning what? So imagine there are two fundamental entities. These two entities can be connected. That connection, we call it in a regular world, but rather in the case of quantum, we call it as entangled. These two objects, fundamental objects, are entangled, connected together, even though they are at a distant location. That's what is called locality to non-locality. Next, the other important feature of the quantum world is moving from deterministic laws to the probabilistic laws. What is meaning of that? See, in the case of the classical computers, and classical algorithms that what we run, these are all deterministic, right? When you run a particular algorithm with a given set of inputs, when you run it multiple times with the same input, you get the same output. Whereas in the case of quantum, it is probabilistic in nature, right? So what happens in the case of quantum, few seconds back I spoke about the superposition, where in which a fundamental unit being there in a state of multiple states. But when you measure it, finally it comes to the which state is not deterministic, rather it is a probabilistic. That's what is the meaning of moving from deterministic class to the probabilistic class. Similarly, there is another interesting feature of the quantum world called moving from certainty to the uncertainty, right? So in order to understand this particular philosophy, you need to understand the famous laws given by, our famous theorem given by Heisenberg, who is the German scientist, who said that there is a fundamental limit to the precision with which certain pairs of physical properties of a particle can be known simultaneously. Meaning, the more accurately you know about a particular particle's position, the less accurately you know about its momentum. That is the loose definition of the Heisenberg uncertainty principle. Meaning what? Imagine that there is a moving train, right? Think that that is a particle. There is a moving train moving with a particular velocity, right, at a given point of time. So say take an example, it is traveling at about 120 kilometers per hour. Now, if suppose somebody asks you what is its speed, you will tell its speed. But if suppose somebody asks you what is its exact position, you may not be able to tell precisely this is the position, because at any given point of time, the object is in its movement. So precisely you cannot tell until and unless the train stops. So this is called Heisenberg uncertainty principle, saying that the more accurately you know about one of the property, say take an example, I'm talking about the speed of the train, then you can tell less accurately about its position, or vice versa, right? If you tell its position, then meaning that you cannot tell exactly what is its speed. So this is called kind of uncertainty principle. The quantum computers deal with uncertainty, right? We move from certainty to the uncertainty. So these are all the features of the quantum world. To sum up, so we spoke that we are moving from real numbers to the complex numbers in the state of quantum computers. Similarly, it's not that a fundamental unit is in a single state, rather it would be a superposition of states. Computation happens from locality to the non-locality. Algorithms deals with probabilistic class rather than the deterministic class, and the computation happens from certainty to the uncertainty. So these are the fundamental features of the quantum world, right? So when you read later on, when you happen to read a course or do a programming or enter into this, so these fundamental properties you should understand. So meaning what? So what happens in quantum physics? A particle can do more than one thing at the same time. So look at this. If you look at this, the left side one is, sorry, the left side one is a simple example or an analogy for the typical classical bit. So you can see that it is happening, either 1 or 0, right? So you can have a bit showing either 1 or a 0 at a given point of time. So this is a classical example, classical bit example. Now, whereas in the case of quantum, on the right side, you can notice, each one is a quantum bit. If you think, so this is one quantum bit, this is another quantum bit. Sorry for the pointer. Yeah, 1 minute. So this is one quantum bit, this is another quantum bit. You can see that both of them, right? So both of them are joining together, showing that they work, quantum state. They work in a quantum state. We will see what is this quantum state, right? So if you look at the conventional computer with a classical bit, it takes 4 separate calculations to run through all possible combinations of the 2 bits. So what are the possible combinations of 2 bits? Like 0, 0, 0, 1, 1, 0, 1, 1. So you require 4 separate calculations. So when you have the more number of calculations. As the number of calculations grow, exponentially you require as many more bits as required. Whereas in the case of quantum computer, all these calculations can take place at the same time. So this is another simple visualization. So if you have two classical bits, so you can see 0001 and then 10 and 11. Whereas in the case of quantum, when you have two bits, I'm saying bits for now, but typically they are called qubits. So you can have all possible combinations of 0001 1110 at a same time. That's the underlying point. So this gives you a quantum speed up, because you are going to have all four possible combinations at a time. Now, you can go back few slides and think of a coin and then the six-sided dice you have, right? A coin is giving you either head or tail, whereas dice is giving you the six possible states. So with all four possible combinations being available to you at a time, you can encode as much information as possible, and which is more than the classical bits. That's the analogy you should understand from the previous slides on the classical the coin and as well as dice, right? So this is the quantum speed up that we can gain through the quantum computers. So if you compare what is the difference between classical computing and as well as quantum computing, if you see, information is stored in a fundamental unit called bit. Here it is called qubit in the quantum computing, right? So in the previous slide, when we said that you have this is classical bit and this is a qubit, this is the fundamental unit of quantum computer. This you should regard it as a qubit, right? So you have a qubit for quantum computing. For processing the information, we use logical gates such as AND, NOT, OR, etc. Whereas in the case of quantum computers, we use quantum gates, right? So the gates are fundamentals for the circuits. These circuits in the quantum classical computer are governed by the classical physical properties, whereas the quantum computers, the circuits are governed by the quantum mechanics and the principles few seconds back I have mentioned, right? Similarly, how do you represent the information in the form of 0 or 1? Here you are going to have the representation in the form of 0, 1, or combination of both. That's the beauty of this, right? You are going to have Boolean algebra based operations. Here you are going to have linear algebra based operations. If you compare the advantages, the classical computers are having certain advantages and solving some of the classical problems like day-to-day our operations. The quantum computers are typically faster than classical computers, and they can handle certain class of problems that conventional computers cannot solve. One of the typical problem is the a random search in a highly unstructured database. So that's a beautiful example of exponential power that you can use from the quantum computers to solve the problem. Similarly, when you look at the disadvantages, of course, classical computers cannot solve some of the problems like integer factorization, etc. Whereas, on the side of quantum computers, you have certain issues because of the errors in computing, right? So let us move on to the fundamental unit of quantum computer, which is called qubit. We represent that qubit in the form of this particular notation, which is called Dirac notation. So this is called Ket notation also. So this is the qubit with the state 0, and then this is the qubit state 1, right? So qubit state 1. So you can represent the state 1 as the qubit. This is called Ket. So this representation is called Ket. So you write either 0 or 1. So this is the representation for the qubit in a quantum computer. So if you have, imagine, 2 qubits, right? You can write it as 2 qubits with the Ket notation as 0, 0, 0, 1, 1, 0, and then 1, 1, as shown here. So you can see that with the 2 qubits, all the 4 basic states of the 2 qubits from 00 to 01 you can have in parallel at a time. You scale it up. Imagine if you have a 3 qubit system, all the states of 0002 111 you can have them at a time. That is the beauty of the quantum computers. You can escalate it. So adding the qubits increases what you can have: exponentially available storage as well as the massive computing power. That massive computing power is basically a parallel computing power, right? And this makes the quantum computers to solve complex problems, right? So imagine that, just to give a glimpse of the difference. Imagine you have a 64-bit computer. You can perform manipulations of 64-bit binary numbers at a time. Imagine if you have a 64 qubit quantum computers, you can perform 2 power 64 dimensions operations at a time. So that's the difference between the classical and as well as the quantum computers that you can have. Now, sir, you said a quantum qubit state could be either 0 state or 1 state, but few seconds back we spoke about the superposition. What is that? I said superposition means a combination of both states 0 and 1. So you can see here one of the superposition state. You can see here that the qubit 0 is in a superposition. Qubit is in a superposition state with a with a with a probabilistic amplitudes. These are all called amplitudes or coefficients. This 1 by root 2 is the amplitude or called coefficient of the qubit state, right? So now this particular state is called equal superposition state. Now if I take it to the 3 qubits, the 3 qubits equal superposition state, you can see that 000 with 1 by root 8, 0001 with 1 by root 8, so finally 111 with 1 by root 8. So these particular entities are called probabilistic amplitudes, right? So now you are having a 3 qubit system in a superposition state with all possible combinations, and these particular amplitudes, these particular coefficients are used later on when the system is being measured, right? So as I said, how do you generalize that superposition statement? Of course, I can represent that in the form of a wave equation or a wave expression represented as psi is equal to this alpha naught and alpha 1. As I said, alpha naught and alpha 1 are probabilistic amplitudes, or when it comes to computing, they are the complex numbers. That's where a few minutes back I said about, we are moving from real numbers to the complex numbers. So now you can see that a single qubit, which is in a superposition state of both 0 and 1, meaning that the qubit psi is in a linear combination of, you can say superposition as the linear combination of both 0 and 1, and their probabilistic amplitudes are given as alpha naught and alpha 1, right? So a qubit which is in a superposition state is at the same time, which is in the superposition state of same time. So this particular superposition generally is explained through a particular example called Schrodinger's cat. Imagine that there is a black box. Imagine that there is a black box, and in that black box there is a cat. Okay, so now the point is, you do not know whether the cat is uh, whether it is having life or whether the cat does not have life, meaning whether it is on live or dead. So you can say that cat is live and cat is dead, so both live or dead, but you do not know what is the chances of having the life or dead. According to your probability, you can code that probability on these amplitudes. So the classic example of the superposition is the Schrodinger's cat in a black box. So both living or dead cat can equally be represented through laws of quantum mechanics, right? You do not know whether the cat is live or not. Whereas in the case of classical, you should tell whether cat is live or dead. In the case of quantum, that gives you the beauty of handling with uncertainty, so that you can represent, you do not know whether it is live or dead. So you can see that the kitty is live with the probabilistic amplitude of 1 by root 2 and dead with the probabilistic amplitude of 1 by root 2. So you can represent this through the superposition state, right? Next property of the quantum computing is called decoherence. Decoherence is a phenomenon which is talking about the loss of superposition, right? When qubits interact with the environment, right, that makes the qubits lose the power of superposition, right? Meaning that when you see that you have a superposition coin having both heads and tails, when you have a decoherence, that would either settle down to heads or tails. You can see here it is in the superposition state. Due to the decoherence, it falls into the either heads or tails, losing its quantum properties. When you lose that quantum properties, what we call that as called measurement, right? So meaning what, in a quantum system, when it is in perfectly isolated state, it would be in a coherent state, right? Coherent state means it is in a quantum state. Now during the decoherence, what happens is you are losing the quantum properties, and hence we call that as measurement, right? So now you can look at this. Imagine I have a single qubit and represented in the form of the wave equation like this, right? Xi is equal to alpha naught, the qubit state 0, qubit state 1. Now when you measure it, what happens? The qubit psi would fall either to 0 or to the 1, meaning it becomes to the classical state. So a qubit which is in the superposition state, after measurements, falls into either 0 state or 1 state. Now question comes, sir, can you tell me to which state it falls, whether it falls to the 0 state or 1 state? That would be decided based on the probabilistic amplitudes you have, the alpha naught and alpha 1. So the mod alpha naught square and the mod alpha 1 square determine to which state the quantum qubit, the psi would fall on. So take an example. You have, two qubits, right? You have this particular wave equation, if you notice, and these are all the probabilistic amplitudes of the two qubits. Now you can see that what is the probability of the rightmost bit settling down to the 0 state, that you should calculate through the amplitudes of 0.316 square plus 0.548 square. If you notice, this is the probability that 0.4 is the probability that the rightmost bit would settling into the 0 state. So your probabilistic amplitudes determine to which state the qubit would get measured. So this is another interesting phenomenon. So we have seen so far, the quantum properties. We have seen the quantum bit called qubit. Then we have seen two fundamental philosophies called superposition and measurement, and of course coherence. There are other entities like entanglement, interference. For the want of time and to make things simple, I am not covering them here. So we will move on to the next important topic called quantum gates. So we have seen qubits. In computing after bits, what you have are gates. So in quantum computers also you have gates called quantum gate, which are based on quantum logic gates, right? They are the fundamental for the quantum circuits, right? So what are these gates? Let us see. One of the fundamental gate, I'm not covering all gates, but just to introduce the gates which are built on top of the qubits, I'm giving you one or two gates. One of the fundamental gate is called Hadamard gate. What is this gate will do? It operates on a single qubit, and when you apply this particular gate, the qubit lead into the superposition state. So take an example. I have the 0 qubit with state 0. When I apply this particular Hadamard gate, it enters into the superposition represented in the form of the Dirac notation like this. Few minutes back we spoke about this. Similarly, if you see, if I have a qubit with state 1, if I apply Hadamard gate, it leads into the one superposition state in this form. Sir, how do I apply Hadamard gate? What is that Hadamard gate? In quantum computing, the gates are typically represented through the matrix representation. So this is the matrix representation of the Hadamard gate, right? So if you notice this Hadamard gate, with this unitary matrix of 1 by root 2, 1, 1, 1 minus 1. So when you supply the input gate of input state of 0, you will get the output of in the form of a superposition state. Next, you have the another gate called Pauli gate. If you notice, if I give the if I apply Pauli gate to a qubit state 0, I get the qubit state 1. Similarly, if I apply Pauli gate on the qubit state 1, I am getting output of qubit state 0. Meaning what? This particular Pauli gate is nothing but a typical NOT operation in our regular conventional computers. So how do you represent that particular gate? Through the matrix called 0110, right? So you can see this is the circuit representation. In the previous slide, you would have seen the Hadamard gate is represented in the form of H. The Pauli X gate is represented, circuit is represented in this form. You can see here, imagine if I am taking the qubit state 0, how would I write that state? 1, 0. So if you apply the Pauli X gate, you can see that output is 1. So if I take 1, my output is 0. So it's typically working it in the form of a NOT gate, right? So you have another interesting gate called C0 gate. What is the C0 gate job? It acts on 2 qubits. We have seen Hadamard, the Pauli, which acts on single qubit. Here, the C0 acts on the 2 qubits. So if you see here, how it operates is, if among the 2 qubits, if you apply on the control qubit is set to 0, then target qubit, you will get the same output that of the previous state. In case, if you apply the control qubit is set onto the 1, then target qubit is flipped. Look at here. So imagine that I have a 0, 0, right? So if my control is set to 0, if this is my target, what is the target I am getting? I am getting the target as 0. Similarly, if control is on 0, what is my target I am getting is the same output. Whereas if my control is on 1, my target is becoming flipped, right? So 0 becomes 1. Similarly, control is here, target is become flipped. So this is called C0 gate, right? This is the matrix representation of C0, and this is the circuit representation of C0. In fact, the C0 is equivalent to your classical XOR gate in a classical computer, which is a reversible XOR gate, right? So these are all various quantum gates that we have, from Pauli gate to Hadamard gate, phase gates, Toffoli gates, like this. And these are all various matrix representation of these gates. Of course, we all know about the classical gates. So these gates help us to operate on the qubits. So we have seen qubits, we have seen quantum gates. Next, we have quantum circuits. What is basically a quantum circuit? A quantum circuit is a model for a computation in which computation is happening on the sequence of quantum gates, right? Now we have seen the quantum gates. So when you have a sequence of quantum gates that are applied in the form of the circuit, you can have the quantum circuit. I'm not going to explain these quantum circuit in the interest of time. So we have seen qubits, we have seen quantum gates, we have seen quantum circuits. Next, you can use these, exploit them for the computational purpose through quantum algorithms, right? So obviously, when you have the bits and you have the gates, you have the circuits. In order to compute, you need to have algorithms, right? So there are various quantum algorithms, especially for solving some of the mathematical problems, solving some of the searching related problems, and they have enormous impact on security related problems. You can just have search or look at them, what are the impact of these quantum algorithms on the information security. What these computational gains we can have? We can have quantum parallelism. We can have the entanglement capability and exploiting the dimension of the Hilbert space, which is the complex vector space that we have not discussed, but this is the fundamentals, right? So what is the advantage of these algorithms? The advantage of the algorithms, when you compare classical algorithms, typically, we look for the polynomial deterministic algorithms, right? So we look for the problems that are solvable by a deterministic classical algorithm in a polynomial time. Typical examples such as matrix multiplication, sorting the numbers, and all that. In the case of quantum, these algorithms, we look for not polynomial time simply, but rather bounded error quantum polynomial time. Meaning what? Even the quantum algorithms also should execute in the polynomial time, but it is bounded error quantum. So meaning you should be able to solve the problem in a polynomial time, but with a bounded error. Meaning that, it's not that your result is deterministic, but it is a probabilistic, meaning that probability of obtaining the correct result is out of 3, 2, right? So you can do the repetition of this execution of the algorithms so that that error can be reduced. No, you might be hearing in the news that quantum computers are being built by various companies. If you look at how the quantum computers look, especially you can see nowadays the IBM has released their quantum computer, and those images are visible across the internet, and then you can access them. In addition, various other companies also have their own quantum computers. Of course, building the quantum computers are through different technologies. So anyway, that is beyond the scope of the this particular talk. Now, sir, so far we spoke about quantum fundamentals. Then we went to the qubits. Then we went to the q gates, right? We have seen q gates. Then we have seen q circuits are there. Then we have spoke about quickly about q algorithms, quantum algorithms, right? So how do I implement, or what are the are there any kind of interfaces, platforms that we have? Of course, there are widely available platforms from IBM. You have IBM Quantum, which through the programming interface called Qiskit, which is built on top of Python. You can use this IBM Quantum environment and the platform, and then try to write programs. And if you see, in fact, you have, of course, a free and as well as the paid, meaning subscription-based access to the IBM Quantum. Of course, you have the simulators that there are about Qiskit textbooks. You can use for the educational purpose and learning purpose, right? And also for building the applications. From Amazon, there is another platform called Bracket, right? So you can access through pay-as-you-go mode. Of course, there is an SDK also, Bracket SDK. It supports various hybrid workloads. You can have machine learning integration with this particular platform and perform the optimization tasks, and classical quantum algorithms can be executed in the Amazon Bracket. Similarly, from the Microsoft, you have Azure Quantum. Again, you have programming interface with the Python and as well as Q#, and you can do a lot of algorithmic simulations in this. Then from Google, you have Quantum AI. The interface is SIP, and as well as the Python programming language on top of that you have, right? You can have a lot of use cases. Quantum walks, implementing the quantum algorithms can be done, right? So D-Wave is another platform where in which you have Ocean SDK, Python-based libraries to implement the quantum algorithms and programming. And another interesting, the platform is Nadu Cloud, where in which you can have Penny Lane as the programming interface, and you can solve chemistry related problems, quantum machine learning problems with this particular platform. So these are all the various platforms that students can explore. So before we jump into the other topic, the let me talk about few myths about quantum computers. People talk that some of the people say that the no quantum computers are not available commercially, and it may take some more time. But remember, as I said few slides back, you have quantum computers are being built and they are even commercially available. Of course, there are certain bottlenecks, but there is a large set of people who are working to make the quantum computers commercially viable, available, and then soon we are going to have them. Another interesting myth about the quantum computers, especially about the qubits, is people say that qubit can be at a 0 and 1 at the same time. Now, in fact, this is a very loose statement. What actually we should say is a qubit in a superposition of state, meaning that it is in the linear combination of real and imaginary numbers, meaning what psi is equal to alpha naught, the qubit state 0, alpha 1, the qubit state 1, right? So this is the linear combination of both 0 and 1. So it's not that just 0 and 1 at the same time. This is another myth which people either in the understanding they talk, right? Another interesting myth, people think that no, since quantum computers have come, they are going to replace the classical computers. It is not so. All our day-to-day activities of whatever we are doing, right? Simple programming, doing the desktop browsing, or making use of our word processing or Excel, all that, you should have your own classical computers, right? Similarly, quantum computers solve all the problems? Certainly not. There are certain problems where quantum computers only can solve, but it's not that it can solve all problems, right? Another interesting myth about the quantum computers is that the quantum computers are going to destroy our security, destroy our encryption, or rather, some people say that no, quantum computers will provide foolproof security. This is again a myth that the quantum computers, yes, impact our encryption, especially the public key cryptography, but at the same time, there are about post-quantum cryptography algorithms and quantum safe algorithms which have come out, so that your encryption and all that, they are becoming safe because of the quantum safe algorithms, right? And similarly, it's not that quantum computers provide foolproof security, but we should have our own security controls and measures in place in addition to the quantum computers. Similarly, many students and many professionals think that quantum computers are some hi-fi physics, and they are only for few set of computer science people. It's not that. Quantum computing is purely interdisciplinary field, wherein which people from physics, people from computer science, people from mathematics, they all should work in tandem. So you need a multidisciplinary team that works, and hence people from all areas can contribute to this particular exciting field. And if you look at the market, it is expected that in the upcoming days, this market is going to quantum computing market is going to enhance and explode like anything. Especially, people expect that by 2032 it is going to touch about $64 billion of market in the global level. That's what is an estimation. It's only to indicate that there is a huge potential for this particular area. Now imagine, as a student, what I should do, how I should proceed, what are the pathways to the career in this particular exciting field. Fundamentally, you need to understand the principles of quantum computing, understand the philosophies and the core principles behind the quantum mechanics, quantum the physics. Then understand the fundamental mathematics behind it, which is coming from linear algebra. This is very, very essential if you want to enter into the quantum computing as a career. And then, of course, you can have relevant skills can be obtained by doing certain, the courses, or getting the training in the various platforms, getting exposed to the platforms and practicing in that particular either in the Qbits or a penny lane, that would actually help. And in addition, there are certain formal degree educations that are being there by various institutes, you can do. Fundamentally, you should gain as much practical experience as possible, play with the systems, and do some internship or projects, right? That is what is important. And in addition to that, finally, you should have networking with the professionals, both from academia and as well as industry. Connect with those experts and peers, talk to them, get the ideas and inspiration, and then you can keep yourself staying informed and as well as adaptable as per the technology is concerned. These are the things that a student who is interested to pursue the career in the quantum computing area, right? So with this, I would like to thank everyone for having the patient listening, and if any queries are there, I would be happy to take it up. Any queries? Will build is basically in a matter of time, right? But if you look at, for me as an academician or as a researcher, we need to go a long way in the sense to make it available with large number of qubits being made available, that there is they work in a noisy free, meaning you will not have decoherence. So that is another interesting thing. Then in my opinion, if you can achieve both noisy free and as well as decoherence, down the line I think maybe in a down the line of 5 to 5 years, right? So but when it comes to being made available to the public, see, as and when the companies are accumulating the qubits, they are making their the quantum computers available to the users. So when I've shown you one of the slide where the various platforms, you can access the real quantum computer through the cloud, right? As an end user, we may not actually require until and unless you do a rigorous scientific computations and calculations, and your problem demands it. But rather, you can always connect to the quantum computer being there on the cloud, and then do your simulations and run your algorithms, right? So getting into the end user, it may take time, but even if it is available for an end user, on a day-to-day basis, it's like kind of a mobile device or a kind of a thing. I don't think that there are applications or there are needs for that until and unless, again, they may emerge, right? So we don't know.
Okay, sir. Thank you.
Right, right.
Sir, also I had a follow-up question.
Please.
So what do you think the pricing of it would be like? What would the presumed cost be according to you?
No, again, it depends upon the companies, right? See, now some of the platforms are being given at free for a few minutes or maybe few hours, and after that, every company, every platform has their own billing price. But as we move on, as the technology emerges and evolves, certainly these costs would come down when there is a competition.
Okay, sir. Thank you.
So any other questions? So So if there are no questions, thanks for patience listening. And if any of the students are really interested to interact with us, you are most welcome. We'll be happy to, host you uh, as a project intern in our lab, or you can always interact remotely and then do some interesting work. We'll be happy to assist or support you in any way that is possible. This is an exciting area. If you are having interest, please write to us and then connect with us. Okay.
Moving
Sir, we also
forward,
have a
yeah.
question in the chart, in the chat.
Uh-huh. There is a question in the chat. 1 minute.
Yes, sir.
So, yeah, Mohammed Laiban is asking about how close we are to achieving quantum advantage in the real world application. See, look at the, when you look at the applications, especially, there are very, limited number of applications as of now in terms of, the where quantum computers is directly required. But, the community is now coming out with their own applications. Say, take an example, in the drug discovery, people say that, we need quantum computers, if they can assist in identifying the new drugs, right? So it all depends upon, the various the other stakeholders from different domains come out with the problems and say that, hey, look, we have a problem, and then this problem needs to be solved, and then not being cracked by the classical. Then, yes. And of course there are people working on such kind of problems. And yes, already this has come, the technology has come out of the research labs. There are various startups which are working and, building the products. And I think, you may be aware that, next few days there are going to be some conference in Bangalore on the quantum, right? So where, a lot of startups, right, not only the technology giants like IBM, Google, Microsoft, but there are several startups from India itself who have actually coming out with the products. So, yes, it is coming out from the research labs. Yeah, so it all depends upon the use cases and all that. But essentially we have already have certain products in the market in terms of security related aspects, like quantum key distribution kits are there. Similarly, the quantum random number generator kits are there in the market. So you can always Google it. There are startups who are actually working and then bringing the products based on this. Yeah.
So, moving forward, always walk through life as if you have something new to learn, and you will. I hope all of you found today's session as insightful and inspiring as I did. On behalf of RAIT ACM, I would like to express our sincere gratitude to Dr. Aswani Kumar Cherkuri for joining us and sharing his immense knowledge for the fascinating world of quantum computing. Your ability to simplify a complex subject like quantum technology is truly commendable and has surely sparked curiosity among all of us. And lastly, a big thank you to all the students and attendees who joined us today with such enthusiasm. We hope you continue to stay engaged with our upcoming events and keep exploring the world of technology. Until then, stay curious, stay innovative, and keep learning.
Thank you. Thank you. All the best to everyone.
Thank you so much, sir.